जी, आज का टॉपिक greedy algorithms. Again, like genetic algorithms, greedy algorithm is not an algorithm, it's a heuristic because it doesn't guarantees optimal solution, rather a good solution. So greedy algorithm भी heuristic based approach है जो कि strategy पे काम करते हैं कि जो best choice, locally best choice है उसको adopt करते हैं without the guarantee that we will converge to the optimal solution. So the underlying core and crux is I want as many as possible. So makes a locally optimal choice, does not always yield optimal solution, but for many problems they do. Still again, it doesn't guarantee the optimal solution, but for many problems they do get the optimal solution. The guarantee is the good solution. So first of all, we see the activity selection problem. Optimal scheduling of a resource among several competing activities. Scheduling rehearsal times in a music studio. Want to select as many mutually compatible activities as possible. So we want to schedule the activities in such a way that the compatible activity can execute in parallel, and we want to complete these jobs in as least time as possible. So इस चीज का भी ख्याल रखना है कि एक्टिविटीज आपस में कंपैटिबल होंगी तो वो पैरेलली एग्जीक्यूट होंगी, और अगर वो कंपैटिबल नहीं है तो फिर वो सीक्वेंशियल मैनर के अंदर एग्जीक्यूट होंगे, एंड वी वांट टू फिनिश द ओवरऑल जॉब इन द लीस्ट पॉसिबल टाइम. सो व्हाट वी कैन डू इज we sort them with their finish time, and we call this set as S. So these sorted activities based on the finish time are placed in the set S and are ordered as 1 to n. So we put the one with the earliest finish time in the first place, and then we screen from 2, find the earliest one k compatible with 1, put k in the second place. So we place the first activities which has the earliest finish time at the first place, and then from the remaining activities we look for the activity k that is compatible with the activity 1 that has already been placed in the set. So in a similar fashion we screen from k plus 1, find the earliest one compatible with k, put in the third place, and so on. Clear है ये बात सबको? So S is a set of n proposed activity. Each activity I has a start time which is called as Si and a finish time Fi. So with the definite constraint that Si will always be less than or equal to f of I. So a start time of any activity cannot be larger than the finish time of the activity. If we select the activity I, the resource is occupied in the interval Si to Fi. We say I and J are compatible activities if Si Fi intersection Sj Fj is equal to 5. So we are given with the two activities, activity I and activity J. दो एक्टिविटीज आपस में तब कंपैटिबल होंगी जब उनका जो इंटरवल है from the start to the finish of one activity I and the start and the activity interval of this activity J, Sj to Fj wouldn't have any time intersection between them. So तब हम इसे कहेंगे कि दो एक्टिविटीज आपस में कंपैटिबल है. Start time to finish time of I activity intersection we can say that it doesn't overlap with the activity time Sj to Fj of activity J, तब हम इनको कहेंगे ये दो एक्टिविटीज आपस में कंपैटिबल है. Now the greedy activity selector algorithm, start to finish, assume that we have the finish time of activity 1 less than the finish time of activity 2 and so on up till f of n. So greedy activity selector algorithm, n is the length of the activities. We start with the activity 1 and then we set j equal to 1 for i2 to n. We have selected the first activity, then for i2 to n, if si is greater than or equal to f of j, then A is A union I, and we move j to I. So what we are doing is, we have first moved the activity 1, let's suppose, to the activity selector or activity scheduling set A. Then starting from the activity 2, we will look for the activity that is compatible with the activity activity J. How is compatible? That the finish time of any activity I, the starting time of any activity I should be greater than the activity finish time of the activity J. If there is such a condition, then we place that activity I in the final activity selector set. And now we move this activity I to J. Means now we will look for any compatible activity with the activity that have been moved to J. So this is what we have already discussed. That once we place the first activity, then we look for then we look from the remaining activities the activity that is compatible with the first one. And once we place this second activity, then from onward we look any compatible activity with the second activity, and so on. This is what is being done in this algorithm. Any question? So here are the start and finish times of 11 activities. Activity 1, I is representing the activity identification 1 to 11. Then there is SI start time of an activity and FI finish time of an activity. Okay. So first of all, we take the first activity, which is 1, and schedule it. Its start time is 1 and its finish time is 4. So we have placed the first, and this is definitely ordered based on the finish time first. So after sorting based on the finish time, we see that the activity at the ID 1 is have a starting time of 1 and a finish time of 4, which is the earliest finish time. So we will schedule this activity, and here is this activity 1 to 4. Next, if we look at the activity 2. Activity 2 has a starting time of 3 and a finish time of 5, which is not compatible with activity 1. And similarly, the other activity 0 to 6 is not compatible. 5 to 7 is compatible. 5 to 9 is compatible. 6 to 10, 8, 11, 8, 12, 2, 13 is not compatible. And again, 12, 14 is not compatible. So after this, we have in the sorting, this sorted list, we have the earlier activities that is compatible with the activity 1 is activity 4. So we will schedule the activity 4 here. We have scheduled the activity 1, activity 2 is not compatible, activity 3 is not compatible, and the activity 4 is compatible. So we schedule the activity 4 here. After we have scheduled the activity 4, its finish time is 7. We will look for any activity that has a time of a starting time of 8 or greater. So we will have activity 8, so we'll schedule the activity 8 here. And similarly, the finish time of activity 8 is 11. So what we can schedule after 8 is any activity with the starting time of 12. So we will schedule activity 11. In this manner, we schedule the activities based on the earliest finish time ordered set. Any questions? So the activity picked is always the first that is compatible in the sorted list. Greedy algorithms do not always produce optimal solutions. So running time for sorting n activities by their finish time is O n log n, and for greedy activity selector is order of n. So if we want to sort these activities based on their finish time, you can use my sort, and it would take O n log n time. And for the greedy activity selector algorithm that we have used, the time would be O n, as we have to select each activity in order to schedule it. So n log n would be the sorting time, and after that, in order to schedule these activities, this would take order of n time.
सर इसमें हमें कैसे पता चलेगा कौन सी एक्टिविटी कंपैटिबल है?
ये तो हमने बात की है इससे पहले। एक्टिविटीज तब कंपैटिबल होंगी जब एक एक्टिविटी का, फॉर एग्जांपल एक्टिविटी I and J are compatible if SI to FI intersection SJ to FJ is 5. जब दोनों एक्टिविटीज आपस में ओवरलैप नहीं करेंगी टाइम इंटरवल के हिसाब से, तब हम कहेंगे दो एक्टिविटीज आपस में कंपैटिबल। या इन अदर वर्ड्स, finish time of one activity is less than the start time of the subsequent activity, then we would say that these two activities are compatible with each other.
सर इसमें एक जो है एक्टिविटी फिनिश होगी तो उससे जो थोड़ा सा ग्रेटर होगा नेक्स्ट वाली एक्टिविटी का जो स्टार्टिंग
वो उसके साथ कंपैटिबल होगी,
थोड़ा वो कंपैटिबल होगी।
डेफिनेटली।
थैंक यू सर।
यानी कि फिनिश टाइम ऑफ द प्रीवियस एक्टिविटी should be less than the starting time of the next activity, तब हम कहेंगे वो दो एक्टिविटीज आपस में कंपैटिबल। जी और कोई क्वेश्चन? Algorithm greedy activity selector produces solutions for maximal size for the activity selection problem. हाँ जी, कौन बताएगा? हाँ जी कुरुतलैन, आप बताएं, व्हाट इज दिस मैक्सिमल साइज? क्या होता है मैक्सिमल साइज? जी कुरुतलैन, जी जी।
सर जो ऑप्टिमल ना हो लेकिन ऑप्टिमल के थोड़ा नजदीक तरीन हो, मतलब गुड सॉल्यूशन प्रोवाइड करता हो लेकिन वो ऑप्टिमल ना हो।
राइट जी सैरिश, इसको और एलैबोरेट करें कैसे? व्हाट इज मैक्सिमल?
यस सर, ये ठीक कह रही हैं। जो मैक्सिमल होता है हमारे पास ये लोकल मैक्सिमम देता है, और जो मैक्सिमम होता है वो हमारे पास ग्लोबल मैक्सिमम देता है। मतलब वो ऑप्टिमल सॉल्यूशन देता है और ये गुड सॉल्यूशन देता है।
राइट। सो मैक्सिमल मींस कि जिससे बियॉन्ड आप जा ना सके। ठीक है, आप किसी प्रॉब्लम में स्टक हो गए हैं, जैसे हमने पहले भी डिस्कस किया था कि फॉर एग्जांपल maybe the optimal GPA that we can obtain in and this department is 4. But given the condition, the family constraints, the other commitments, or job constraints, let's suppose we can't go beyond 3.7. So then this 3.7 would be the maximum. Maximum वही है 4. बट हम जिन कंस्ट्रेंट्स के अंडर वर्क कर रहे हैं उसमें हम अचीव नहीं कर पा रहे, तो हम जो अपना मैक्सिमम अचीव कर पा रहे हैं, दैट वुड बी द मैक्सिमल. So maximal is a good choice, a local optimal, but not a global optimal. So for the these activities 1 to n, suppose there is one solution A for the activity selection problem, Km and sum on an ordered list of these activities. If K equal to 1, theorem is right. If K is not equal to 1, F1 is less than or equal to F of K, then 1 is compatible with the rest of A to K. Okay. A minus K, sorry. Theorem is right. If K is not equal to 1, okay, this is a simple theorem which says that if K is 1, theorem is right, definitely it's right. And the theorem is that an activity that has been scheduled earlier is compatible with all the subsequent activities in the list. If, let's suppose, finish time of activity 1 is less than the finish time of activity K, so it means finish time of 1 would be less than the finish time of all the activities that are beyond K or after K, right or wrong?
Would you build a website for a major brand?
Right, sir.
So 1 is compatible with all the activities, with the rest of the activities in a K. So A minus K list is compatible with the activity 1. Clear हुई बात सबको ये?
Yes, sir.
Okay. So again, elements of the greedy strategy in general, there is no way to tell if greedy algorithm is solve a particular optimization problem or not. But there are 2 ingredients that are exhibited by the most problems that lend themselves to a greedy strategy. First one is the greedy choice property, and the second one is optimal substructure. Optimal substructures we have already studied in dynamic programming, how we see optimal substructure. If we want to find the optimal solution to a problem, then this would comprise the optimal solution to its sub-problems. And we see the greedy choice property is a global optimal solution can be arrived at by making a local optimal choice. The properties where greedy algorithms differ from the dynamic programming. So greedy choice property says that we have to take a local optimal choice or a greedy choice, or this is what is different between the greedy algorithms and dynamic programming. Dynamic programming में क्या था? ये बच्चों, उसमें भी एक ऑप्टिमल सबस्ट्रक्चर प्रॉपर्टी थी, दूसरी चीज क्या थी?
सर डायनामिक प्रोग्रामिंग में प्रॉब्लम
जी
सर डायनामिक प्रोग्रामिंग में प्रॉब्लम्स होती हैं वो इंडिपेंडेंट नहीं होती, और जो डायनामिक प्रोग्रामिंग है वो पॉलिनोमियल टाइम लेती है।
ठीक है, लेकिन 2 प्रॉपर्टीज में सेकंड क्या थी वो याद है किसी को? एक तो हम देखते थे कि ऑप्टिमल सबस्ट्रक्चर हो, दूसरी क्या थी? डिपेंडेंट सब प्रॉब्लम्स।
Yes, sir.
ओके। और यहाँ पे डिफरेंट ये है कि यहाँ पे हम एक ग्रीडी चॉइस प्रॉपर्टी यूज करते हैं, जो कि ये कहती है कि हमने हर स्टेप के ऊपर एक ग्रीडी चॉइस लेना है, एंड देयर शुड बी ऑप्टिमल सबस्ट्रक्चर, means that the solution to a problem is dependent on the solutions to the sub problems. So greedy algorithm make whatever choice seems best at the moment. The choice depends on so far not dependent on any future choice. And in case of dynamic programming, the choice at each step depends on the solutions to the sub problems. Clear hai?
Yes, sir.
Again, the optimal substructure property, a problem exhibits optimal substructure if an optimal solution to the problem contains within it optimal solution to the sub problems. So अगर हमने किसी problem का optimal solution लेना है और that carries a substructure property, then this means that the problem A can be divided into the sub problems, and the solution to those optimal solutions to those sub problems will lead to the optimal solution of the problem. So again, the optimal substructure property states that if a problem can be divided into the sub problems, then the optimal solution of the problem can be obtained by getting the optimal solution to the sub